The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Our investigation of stochastic gradient descent. This time we'll be talking about the stochastic policy interpretation, and I have some examples, well, a very simple sort of system example, but a whole bunch of different ways of looking, like fooling with it in policy parameterizations that'll hopefully give you some feel for how to actually go about using this if you want to use it in your project or something like that. All right. So here. Okay. So I gave a little introduction to the idea of a stochastic policy last time, but this time I'll give maybe a little review of the things and also a sketch of the algorithm. I think Joe asked for pseudocode. You get a feel of the process you need to go through. So you're just in sort of words. This is the process. I'll just get right into it. Set alpha. And again, there's a bunch of ways of actually implementing this and going through the details of it, but this is a very simple way and easy to understand. And most of the other forms are pretty clearly derived from this, but you can sort of tweak it maybe to get a little bit better performance or fill in the details in different ways. But so set alpha to an initial guess. Wow. Sorry. So this is what you start your policy off as. You can start as 0, as a bunch of random numbers. And this can affect your result a lot, actually. Good initial guesses will obviously converge faster, but also they can be in different basins of attraction for different local minima. So it also makes sense sometimes to run it several times from different initial guesses and just see where it goes. And if they all converge to the same thing, that means you're at least in a local minima that has a large basin of attraction. While if they go to very different things, that means that you sort of have a local minima problem. And you can take the minimum of all those runs, or you can try to sort of investigate exactly why you keep on getting stuck. But so the initial guess isn't just like come up with the best thing you can. It also means sort of map out the space of policy parameters somewhat, so that when you get stuck in a local minima, you have some confidence about how good that policy really is. So then this is, again, you don't have to do this, but run policy pi alpha. So this is the policy with your parameter set of your alpha. And store the cost as your baseline. All right, so that gives you your first baseline. Then, let's see, we have a do while loop here. So do. So draw noise z. So if you remember before, maybe I should sketch this first one. I'm going to fill both these boards with this sketch. Z is the noise you add to your policy. So when you're searching, that's the when you sample, right? That's the vector you add. I'll write out the details of it over there. So draw your noise z from some distribution. Now, yesterday we talked about the example of a Gaussian. That's a common one, but there's a number of other ways. And actually today we'll talk about a different distribution and sort of why you'd want to use it. Run system with pi alpha plus z, right? So this is sort of when we're evaluating how well that policy does. And then we'll say we'll store this in what I have. Store this as just, we'll just store it in J. All right. Now we do the update rule that we were talking about. So alpha gets alpha plus negative eta j minus b. All right, b is our baseline up here. So j minus b z. All right. And then update your baseline. Now you can do this with a second run where you run your new policy. That's sort of the more expensive way, but you can have confidence in that baseline as long as it's not too random when you evaluate the system. You could do a decaying average. You could have, for example, B gets 0.2 times your J plus 0.8 times your old baseline, right? And so in this one, it's sort of an exponentially decaying average where I take my new one, smooth it out by averaging it with the previous one. And then if you think about what this does, sort of every measurement gets sort of exponentially decayed away in its significance as you go through time. So you update. And then you can do this while not converged. Many times you can just do a for loop too, and you can just run it for 100 iterations or several hundred iterations and see whether or not it looks to have converged. That's what I often do, but this is really what I guess what you're doing. It's just the for loop and stuff is sometimes easier, and it prevents you from getting stuck where your convergence conditions never met. You have to control C. So, right, so hopefully that this is clear enough that if you wanted to implement this, you could go do it and try it for your project if that's what you're interested in. All right, so. Oh, sorry, this is et cetera. There's different ways you could update your baseline. You could do it with a, yeah, sorry. I mean, these are two common ones. I mean, these are the two that I usually use are these, but you could have critics and stuff like that too, where you have more complicated updates for having a more complicated baseline. So, all right, so when should you use this? We'll just say stochastic gradient descent. All right. Well, it's important to remember, one, that it never does better than true gradient descent. So if it's cheap to evaluate the true gradient, you can follow that true gradient down, and you'll be in pretty good shape. Now, the fact that it's random maybe gives you some robustness to very tiny local minima, but you could add that in your gradient descent too if you're just to bounce yourself around a bit. So stochastic gradient descent, if you have an easy way to compute the gradients, you can do gradient descent using those, or you can even do something like SNOPT or some higher order method. So if it's easy to compute the gradients exactly, it doesn't necessarily make sense to use stochastic gradient descent. If those gradients are impossible to compute or extremely expensive to compute, then it can make sense. Then also, if you have a good parameterization, it can be quite efficient. Again, like, I guess this isn't a prerequisite because it will work with high dimensions and just sort of like and naive parameterizations. Wow. Maybe just. naive params. But it'll be really slow. Or it often is, but is slow, and it can get stuck in local minima. So if you have a good parameterization, it can be much more reasonable to use this. An example is in our lab, we have this glider. They're trying to have perch. So we launch out of this catapult. It flies through, executes a maneuver, and then tries to catch this line. Right? Now, in that case, if your parameterization were the kind of open loop tapes we've previously used, where just, what elevator angle do you try to servo to, that could be a bad parameterization. It's very coarse. It's going to demand sort of rough things. And so trying to do learning on that could be very slow, especially because an evaluation is so expensive. So if we can come up with a good parameterization, though, it suddenly becomes reasonable to do this. If we can knock down to 5 parameters that parameterize a very sort of nice class of policies, now maybe we don't need that much data, and we can actually get it just by launching it. So if we can come up with that good parameterization, doing this should work, yeah.
What if you had a good estimate of what your trajectory should be? Do you parameterize with a lot of parameters, or be better?
Well, I mean, if you can start with a good initial guess, which maybe means that you converge reasonably quickly. But the thing is that the learning is going to struggle to get a lot of improvement. Like it'll get some improvement. I'll show in these examples. You can have ugly parameterizations, and it'll still learn a bit. But the problem is that if you parameterize in this open loop tape, right? So let's say we have some really nice smooth trajectory, like this, and we parameterize it. Is this all clear? So this is sort of off in a tangent. But this is just sort of about bad parameterizations. Yeah. So do you want me to go through all this first, and I can talk about the points in detail?
Do you need a microphone?
I believe I have a microphone.
Is that?
Yeah.
Okay.
All right, thank you. All right. So are we all on board here, or are we? Yeah. Okay. Good. Yeah. This is sort of so if you parameterize by setting all these numbers, right? So you have a nice smooth trajectory. That's the kind of stuff you want. Now, if you parameterize it by saying each one of these numbers, stochastic gradient descent, when it bounces around, is going to be like, okay, send this guy up a bit, this guy down a bit, these two guys up, this guy down, this guy down, this guy up, this guy practically in the same place, something like that. And then you're going to get some param policy like this, right? Now, your physical system is going to smooth that out. It's going to filter it, right? You're not going to execute something like that necessarily. But it's very unlikely that that's the right kind of policy, right? I mean, it's very sort of fine-grained. It doesn't necessarily make sense. So if you assume you're going to have something smooth, it's nice to use something that's going to be sort of always relatively smooth. Like if you were to use fewer points to parameterize a spline, that could be a win. So that's what I mean by a good parameterization, is something that ideally captures the kind of behaviors you want in your system. Also, so I think the main point is well, this is not the main point. This is a big point that I think a lot of people tend to do, and that I can be guilty of myself, is don't discard backprop through time, RTRL, SNOPT. Many times, because you can see how simple this update is, that it's very tempting just to be like, okay, well, I'll put this loop in, run it, and I'll be in good shape, right? I mean, because it's trivial to write that code. I mean, you can see from the pseudocode here. So when you're working on your project, if you're like, oh, well, I want to optimize, I'll just throw this on there, bam, I mean, it'll take you 30 minutes to get that code running. But, maybe you think backprop to time is more confusing. We have to go enter it as a joint equations and stuff like that. But these give you the true gradient. If your gradients are cheap, doing this can be a win. I mean, you can get a better policy. You can solve it a lot faster. You can check richer classes of parameterizations because it will solve them so quickly. So when you're thinking about, okay, we're trying to solve this problem and you have your project, don't choose this without being very conscious that it has a lot of limitations and there's a lot of alternatives which could be better. So first think, are there very solid sort of things you can do with these using SNOP to converge nicely? If you can't, if you don't have a good model, if your system is too complicated, stochastic gradient descent maybe is what you want. All right, so that's sort of a discussion coming back from Tuesday on when to do these things, and also hopefully code that now that you have it in your notes. Now that you have it in your notes, you'll be able to implement this pretty easily. So now getting on to the new stuff for today, talking about stochastic policies. And in particular, we're going to be talking about a certain class of these kind of algorithms, reinforced algorithms. All right, and I think that these were introduced by Williams, and he's at Northeastern. I think in paper 92 or something. So once again, trying to pass across the idea of the stochastic policy. So this interpretation is very different. We're not going to do the linearization. We're not going to assume, oh, we have this nominal policy. We sample and try something else. We're going to assume that we have some distribution of policy. Oh, our policy is a distribution. So the way you can think about it is we parameterize our distribution with alpha. Our policy then has some stochasticity to it, which is going to give us what used to be our alpha plus z, right? So we don't think about this is not a sample. This is sort of the output of our policy. This is how we represent our policy, not as the nominal action, but as some parameterization of the behavior. All right, so this would be, for example, if I were to play a game where I was flipping a coin and I bet on something, it could be like, okay, my parameter here is the percentage of times I'm going to bet money, on it coming up heads or something like that. I mean, that doesn't make sense because your expected values of everything are 0, or well, net 0 if you're playing a fair game. But the point is that it's something like, this is the probability of me doing this. And so here we're going to think about this as the mean of a bunch of Gaussians. So our policy is do all these actions with the probabilities described by a multivariate Gaussian with means described by this vector. All right. Okay. Yeah.
On the output, you just have alpha plus z. Is the policy just to add noise to your parameters?
I mean, these are the two different interpretations, right? So I mean, it is effectively doing that. I mean, over here where we have our nominal thing, and then we add this noise, right? Then we have our nominal policy. We add noise with distribution like this. But this one, what we have is we again have this is parameterizing a distribution, and our policy is to do these things with this probability, right?
And you said that alpha is the mean.
For us, it's the mean of these Gaussians. But you could parameterize it any way you wanted. You could have, you could have a policy parameterized by, if you have discrete actions, it could be the probability of all these actions and force them to sum up to 1. It could be some parameterization of a PDF or something like that. So we're going to talk about it in a limited case. And I think that thinking about that way, at least for me, it's easier to think about where we're going. But remember, that's a lot more general, that this is just parameterizing some distribution of actions. And so it could be something very general. But if you're having trouble putting your head around what all that means, you can think about it just like this is just describing the means of a bunch of Gaussians, and then our policy is do these actions with the probability described by that. Does that make sense? I think that this is sort of, I feel like I'm running around in circles here. All right, I just want to be clear. So in that case, it doesn't make sense to say, so this goes through our system and produces cost j, right? But now j is a random variable. All right? So it no longer makes sense to say, what is j for this policy? Because running that policy is going to produce all sorts of different j's, right? So when you evaluate the policy, I mean, you could have a question of what is the right way. Should you do the min of j? Should you do, what is the worst j it's going to produce? Or what is the maximum j it's going to produce? Well, the thing that you'll generally choose in this world is, well, not Earth, but our discipline, is you want to look at the expected value of j, right? And so this is a philosophical decision to some degree. I think Russ may have talked about this a bit, but when you're on an airliner, you probably want to look at the min of j. When you're building a gambling robot, maybe you do want the expected value of j, assuming you have a lot of money, right? But so this is a philosophical decision, but it's analytically tractable, and it makes sense in many cases. So, and again, like Russ always says, animals aren't doing like robust control. I mean, if they were, we wouldn't be sprinting around and jumping and doing gymnastics. Well, some people wouldn't be doing gymnastics. I'm probably not doing them anyway. But my expected value of trying to do gymnastics would not be high. I can guarantee that much. All right, so what we're going to look at is our stochastic gradient descent now. Since we can't just follow dj d alpha, we're going to have to look at d expected value of j d alpha, right? So this is now our metric, and so we have to look at the gradient of that expected value. Now, this then, this is the definition of the expected value, right? We can call, I'm going to call this sort of like the policy parameters that you're running on under this, this trial. I'm going to call it beta in an attempt to be as unoriginal as possible. So we're going to call this beta. So the expected value for j, we want to integrate over all beta. And your expected value is going to be, where am I here? Yeah, sorry, I've got an error in my notes. So j of beta, probability of beta. All right, so this is just definition of expected value. Now, if you push the d alpha through, if you push d alpha through for a beta, right, what you're going to find is that j of beta is not a function of alpha, right? We're saying like beta up here, written up here, is a function of alpha. I mean, that's how we've derived it. But remember that beta is just the actions you've chosen from your distribution. So if you look at running your system with these parameters, that's not a random variable. That is just your number, right? So the thing that varies, though, is the probability of getting beta, right? This is the function, this distribution. So this is what depends on alpha. All right. All right. Now, this is where a bit of cleverness comes in. You can write this then. There's an integral over beta, j beta. P, so again the distribution beta, then d alpha of ln of p of beta, d beta, right? So this is just saying when you take the derivative of your natural log, you're going to cancel out this one, right? You'll get the derivative of the one inside. Does that make sense? When you do a chain rule on this, you're going to get 1 over p beta d p beta d alpha. Right? So this is sort of the trick that you need. Right, so you just have to see this. All right. I guess I can erase the pseudocode. So once you do that, if you look at that expression over there, what you can see is that it's the same as the expected value, right, of j beta d ln p beta d alpha. Right? So because we're integrating over all beta, probability of beta. Right? So that's the expected value of this. That means that if we can make this our update, right? If we can make effectively this our update, then the expected value of our update is equal to the expected value, well, the derivative of the expected value of our performance with respect to our policy parameterization. Do you see? Now that's sort of cool, because this seems like sort of a complicated thing, the derivative of your expected value with respect to your policies, other things, because it's this big random thing over a very complicated J, like a general J. We haven't assumed anything about J. We didn't do a linearization. We didn't do anything like that, right? So J is still however general you want it to be. It's not local anything. The derivative of this with respect to alpha, if we can make this our update, we file that derivative. So that's pretty cool, right? So the question is, we have, what does this update look like in practice? This is kind of an ugly term. So what happens when we actually try to do an update like this? Well, we have, we can write this as our update. We want it in the direction of the gradient. It's going to be delta alpha again. Now we want a learning rate, because this is, again, sort of a gradient following thing. So generally in there you want some sort of learning rate. If you're just going to do a gradient descent. Then you can make this J of beta, which, again, now we can write this as alpha plus Z. All right. And then something to represent that DLN, D alpha, P beta. So we'll call that E, right? And we'll say that's called the eligibility. I think that term may come from neural networks, but you can think of it as this eligibility captures how sensitive each parameter should be to an update. So let's say we have 10 alphas, and the eligibility for one of those alphas is very high. That means that if we do well, that eligibility should get should go much more in that direction. The eligibility is sort of just capturing the weights of how much you think each parameter is responsible for affecting that output. Right? So a big eligibility on a parameter means that that parameter is going to move a lot. If the eligibility is small, it's not going to move much at all. Okay. Does that make sense? So that's the way to think about the eligibility. All right. So the eligibility is just capturing what we expect the significance to be. Yeah.
Is it the quantity inside the expected value brackets, or is it the expected value?
It's just this quantity. It's not the expected value.
Okay.
We want our update to be this inside the expected value. Then the expected value of our update is the gradient, right? So it's just the quantity inside, right? So I think I remember when I first learned this, Russ was talking about the eligibility, and I had no idea how to interpret it. And if you still are confused about it, I can try to describe it in more detail, maybe with a picture or something like that, if you'd like. Do people think they have a good idea of what the eligibility means intuitively? Okay, great. Pardon?
I know eligibility choices. How do you calculate E?
I'm going to go through how you calculate it right now. Because EUC is, it's going to be this. It's going to depend on what our distribution is. So I said if we parameterize our policy by the means of a bunch of Gaussians, eligibility is going to be one thing. If you parameterize it as a bunch of Bernoulli variables or something like that, it's going to be different. Right? So it depends on the kind of distribution your policy uses. All right. So, yeah.
Alpha isn't the means of a bunch of Gaussians, and what does alpha plus Z mean?
Z, alpha plus Z is it's always the action you take. Sort of like I actually had some notes on this. If you think about it, let's say that the way you represented your controller Yeah, so there's some subtle differences here, but yeah, I think it's worth going through to maybe. So let's say I parameterize my controller by 3 numbers, like a gain on position, a gain on the speed, and an integral term. So this is a PID controller, right? So this is something that most of you, I think, are probably familiar with. So this is a very simple parameterization of a policy, right? Now this is how we control it. Now, but the thing is that this is sort of what the actions are. So this would be, a beta would be one of these. An alpha, I mean, and this terminology isn't necessarily standard. I think the alpha and ZR of my beta I just came up when I was trying to make these notes so I could have a simple term to write down in all these expressions. But so this is your beta. This is the thing you're running your system under, right? Your alpha is the same size as that, but what it is parameterizations for some distribution of how you select these. All right? So in a Gaussian, I mean, here's a simple, I gave you a simple one, a Bernoulli distribution. This could be, let's say KP was either 1 or 5, then my alpha 1 could be the probability of picking 1. And then the probability of picking 5 is 1 minus alpha 1.
So in this case, it's a specific evaluation of your stochastic policy?
This is a specific evaluation. This is the parameterization that defines the distribution. So once you tell me alpha, I can tell you the probability of getting any of these, right? But when I run it, I have these numbers in there. So this is sort of like a sample for my distribution. And this is what I actually get the cost of. Yeah. All right. And so if you look at this minus this, that's the noise we talk about in the other interpretation. Right. Okay.
The system you're trying to solve is not finite. Like, how do you decide that, like, running with a limited number?
Oh, how do you? Yeah. So that is, we're thinking about this. This is another thing I'd note on. We're thinking about this in the context of trials. So you run the system under a trial, right? And then you evaluate the cost. What if your system is just running constantly, right? Well, you can think about a short period of time as a trial. You could run it for a while. You can look at discounted cost where you, and then there's also I think the average cost or average reward formulation where you can look at how long, what reward you expect to get running it off to infinity, like what sort of reward rate. I think about it right now in the context of, let's just say we can do a trial of something. And if you want to worry about what happens if the system's constantly running, there's ways you can still do like a trial, and then you can keep track of an eligibility trace, which is different than this eligibility. Sorry, I shouldn't. That's a confusing thing. What you can do is if you're running constantly, you can just sort of keep iterating and take into account this sort of coupling reward. Because you can imagine, it's sort of like if I study for my test tonight, I didn't have a good night, but I did well on my test tomorrow, so I was happy. And so it's sort of like then my action didn't give me an immediate reward, gave me rewarded later. That's sort of the delayed reward problem, which is very common. And there are ways of dealing with this here, where you can still just look at your accruing reward like right now, and you can still sort of give yourself reward for doing good things in the past. You can still handle that. So that is a good question, and there's a number of ways to deal with this. But right now, let's just think about execute a trial. All right. So, right. So then our E here, again, to make it look like what we want it to look like, to make it, well, that tells us exactly what our E is. So we can write it as this vector, dd alpha 1 of ln probability of beta. And this beta is still, this vector, but the probability of that is a scalar, right? So this ln of this probability is just a scalar. And that's our entire thing here, right? So then let's say, again, this is where the distribution you choose comes into play. But let's say that we chose our distribution to be a bunch of Gaussians, all the different parameters IID, right? Well, the noise IID. But we'll just think about them as all independent with the same sigma. So the probability of getting a beta, because they're all independent, is the product over all our different parameters, 1 over square root of 2 pi sigma squared. This is going to cramp it if I do that. So I think I have the opposite problem of anyone else. I write way too big. Video people will be happy. So just let me squish it in here. All right. So probability of beta is equal to the product over all my different parameters of 1 over, well, you know, the Gaussian distribution. It's like this. Right. So if you give me a beta and I have the alpha, I can tell you the probability of us picking that beta. All right. So our ln, so the natural log of this, well then, I mean, the log allows you to turn this product into a sum, and you'll get the sum over I equals 1 to n. Now we can take this derivative. This is a constant. That won't show up. And we'll just have the derivative of, there should be a, yeah. Yeah, so the derivative now of this, we'll get rid of this. This one is simple to do now, it's just a product. So the derivative of ln p beta d alpha, oh, I didn't do this again, equals beta I minus alpha I over sigma squared. Now if you remember how we talked about it over there, it ends up being, yeah, they don't need to be I's, these should be vectors. So here, this is our eligibility, z over sigma squared. Now, what does that mean our update is? Now, hopefully this looks familiar. My voice is struggling today. I'm going to come in next time talking like this. Great. So, this is our update. Does this look familiar? Yeah. Actually, let me, yeah, I guess so. Does that look familiar? Is this a no, it does not look at all familiar? Or is this a yes, it looks so familiar, I don't want to waste my time and embarrass myself by saying it does? It does, right? It's the exact same update, right? Now this one we don't have a baseline, and we have sigma squared. But that sigma squared is just a scalar, and we already said baseline or no baseline, whatever you want, doesn't affect it, right? Now, is that true for this case? It didn't affect the other one. This one it also does. If you think about your reward as, so yeah, right. If you think about your reward as 1 everywhere, then your derivative, let's see. Yeah, where is this exactly? Okay, yeah. All right. So if this is constant, right, then our derivative expected value is 0, that means that the expected value delta alpha over here has to be 0 because it's equal to that expected value. That means the expected value of our eligibility is 0, right? So the expected value of the eligibility is always 0. So that means that some constant in there is not going to affect it, right? When we do this expected value, when we put in our baseline, that's going to turn into 0 because the expected value of E is 0. The exact same thing we had previously, right? And you can see this is the case for this specific example of Z. The expected value of Z is 0 again. So it's not going to affect the direction of our updated expectation. So yes, you can do anything like this with eligibilities. You can still use a baseline, right? So that this is really the exact same update that we already found. All right? So I think that's pretty cool. But update that we originally interpreted as locally following the gradient is also following the true gradient, not some sort of like local, but the true gradient of the expected value of the performance of that policy. All right? So if you have some really ugly value function, you throw this distribution on top of it, and you move it around, it's going to be some, it's going to follow in the direction of like true improvement there. And then a little test case, I remember when I was trying to think about interpreting these things back when we were originally doing some of this analysis on the signal-noise ratio. If you think that you have like a little cusp on, like if you have a value function that has a little plateau on it, I can write this on a fixed board because it's not going to stay. Well, if you think you have a value function that's sort of like sitting around here, my drawing is going to be too clear. But here, we'll do it in 1D. If you have like a value function like this, right? You sit here, you'll follow the local true gradient if it's very small. The other one says that you'll follow that the gradient no matter how big it is. So what it's sort of doing when you have this Gaussian is it smooths out kinks and stuff like this in your policy, right? Because you think like my local analysis says, okay, well, I'll just get local enough that these little kinks in my value function aren't a problem anymore. But here we said we didn't say anything it was local. We said it was global. And so it's following this gradient even if we have ugly stuff in our value function. The reason is because this distribution sort of smooths that stuff out. And now we're still able to follow it. So that gradient is still well defined. It takes the stuff and smooths it into something. Does that make sense? I think it's just this big sort of difference in interpretation right here. There's the one where this local analysis and it follows the local true gradient, but only locally. And then we have the other one which follows even, it doesn't require small sigma and everything like that anymore. It'll follow the true gradient of the expected value of your reward. Maybe that's too big of a mouthful for it to be clear just by saying it, but these are the two different interpretations. All right? All right, good.
That Gaussian is basically the policy.
Oh, yeah. So I'll draw this better. So here is sort of our alpha. So our reward. Here we have our value function. Our policy is taking actions with this probability. All right? That's our policy. So you can see that this, even though there's a kink in it, as it moves that over a bit, this is varying smoothly. So even though this is a little disconnect like that, this is going to slide over still smoothly, right? So the gradient is still always going to be nicely well-defined and everything. And this also goes out to infinity. So even if there's some ugly thing way out there, you're never going to like suddenly go and start seeing it when you never saw it before. You always sort of saw it, right? So you'll be following that sort of smooth one all the time. And that's nice because maybe you won't be following, when you get really broad, one interpretation says, well, not in the linear regime anymore, so we're not following that local true gradient. This is sort of the issue that brought it up, is that, let's say, like this one says it's the linear analysis, and it says like, okay, if my sigma is small enough so I sample close enough so it looks approximately linear, I'm going to follow that gradient. But it says break down. When it breaks down, you get this really broad Gaussian. So what does that mean? Well, this one's still following that gradient. So that means that it's just seeing stuff all over, and it's following that gradient instead of this local one, right? Now the problem is that if you follow that gradient, if you end up, that could, the stochastic policy isn't necessarily actually the optimum one to follow. Like when you're actually running your policy in the end, certain systems you do, but in many mechanical systems, you don't actually want these random actions, right? There sort of is the action, there's the actions that actually do minimize cost, right? And so that sort of local interpretation has some value because you don't necessarily want to stick with the stochastic policy forever. That's why you sort of reduce your sigma and you get tighter and tighter and tighter. And you follow the gradient sort of that's more and more biased to get the right spot. Because you can imagine if you have a value function, it's a global min here, and then let's say this is all extremely high, and this goes down and it's like a low plateau. Now if you have a really broad Gaussian, it may say, okay, well, even though that this is the best spot to execute, I'm going to slide way over here because I have a sort of lower expected cost, right? And I could put you in the wrong spot. If it was really tight, then it would say, okay, sit right here. So do you see that? That's sort of the distinction. Is that this broad guy could push you in the wrong direction if it's really broad. And you may not in the end want to execute a stochastic policy for this exact reason. Your stochastic policy could have a much higher expected cost than a small sigma stochastic policy, down to where if sigma is 0, that's when you actually have the minimum expected cost. Yeah.
So when is this used? It's used like when you're starting or when you don't know about a system? Or?
It's when you don't have a model. It's used the same context as the other one. Are you saying stochastic gradient descent as a whole, or?
I mean stochastic policies. I mean,
they're.
That makes sense in poker. So what?
It's used for exploration, right? Because our other one, where we had this nominal policy, we added noise, that doesn't look any different except from this sort of interpretation than this, right? So
for the flapping and learning about systems.
Yeah, it's for exploration. You need it to get more data, right? Because if I run the same policy all the time, I don't know how things are sensitive. Mm-hmm. So my stochastic policy gives me this information to where I can learn, right? So in the end, many times, yes, you'll want a deterministic policy. But for the development of that policy, you'll want to execute all sorts of things that could be suboptimal, but they give you information. And so that is the interpretation here, is for that learning. And if your system is evolving and stuff like that, if it's not constant in time, you may want to always run a stochastic policy because you'll be able to constantly learn, if that makes sense. So you may never want to converge in that. So, but I think it's, yes.
How do you obtain the parameters of that stochastic policy, that probability? It's very sensitive to sigma, right?
How do I get the parameters of what?
Of that distribution.
Distribution? Well, I mean, that's what I've set, right? I said I'm going to act with a probability described by a certain distribution, and I describe the distribution here. So I know these probabilities, because this I set, that's sort of my controller. I designed that myself. What I don't know is this value function aspect.
So that should be based on intuition?
Oh, no. This up here? Oh, how do you decide how broad this is? Intuition has something to do with it. Also, you can imagine sampling. I think I mentioned this on Tuesday. You could sample. You can imagine I sample a few points, and I look at them here, and it looks straight to me. And I'm like, OK, well, what if I sample bigger? And I get like these points, and it looks relatively rough. Then I know, OK, well, I want to be sampling on probably the regime where I'm going to see this roughness to some degree. I don't want to be stuck where it's going to take me forever to go anywhere because I'm in a linear regime. So you can do some sampling and get sort of the coarseness of your value function. And so that's sort of before you run it, you do some of those things and you figure out how big these parameters are. Because the alternative would be you set it, you see how it does, and you fool around with them all the time. That's another way to do it. But this way you sort of have a more direct process for trying to be like, OK, I want to be sampling where I actually get some interesting information. And so you want to be sampling where you're probably getting distributions that cover linear. It's fine if it's linear, but you want to make sure that you sample to where you're going to move around to these different features. You want to sort of be able to you want to be your ADA also. You want your updates when you change your policy to be on this scale too. Because if it was really small, I could take forever to get down to this minimum. Or if I was over here and I had small sigma, I may never sample over here. So I never know to move that way, right? And so like if you have a bigger sigma, you might be able to get out of this local min, because that sample over here, say I did better and move in that direction, despite the fact that locally it was bad. So there's a number of considerations. But yeah, doing some sampling and stuff like that combined with some intuition, it's probably the best I can give you as to how to set these parameters. I mean, that's a tricky thing. That's something that's nice about SNOPT, is there's no eta to set. This one also has a sigma to set. So, that cool? So please, this is, Russ emphasized that I was to make all of you understand this stuff really well. That's why I had 2 days, and if you do it on your project and you apply it at the wrong system, I'm going to be blamed. So yeah. So if you don't have a model and you don't have anything like that, try backprop first if you can. Try SNOPT first if you can, I think. If you can't, this maybe won't do as, this can solve the problem too, I guess. All right, but sort of appreciate its limitations.
With the stochastic gradients and the stochastic policy, you also have to be careful about how you parameterize everything.
Oh, very much.
I mean, you are taking the expectation over these betas, which are in fact instantiations of your parameters. So
that's a very good point. Is that
are you still like having that problem regardless of which two you use? You still have to.
What do you mean, which two?
Exactly how to parameterize.
Oh, whether you're using backprop or this or something like that?
Well, no, between the stochastic policy and the stochastic gradient descent.
Okay, I know. I really want to emphasize something right now. They're not different. Okay.
Right. Exactly. Well,
They're not. They're the same thing. All right. You are correct that your parameterization is going to affect things, because you're going to get to a minimum with respect to your parameterization.
Right.
You're going to be sampling over your parameters, and so the cost function is going to be a function of your parameters. So if you imagine if you have different parameters, the cost function will look completely different, right? Does that make sense? If I were to parameterize with an open loop tape or a feedback policy, how the value function depended on those parameters would be completely different, right? So it's very important that's true. It's over these instantiations of these parameters. So picking that affects everything, and picking a sensible one it can be a hard problem.
So it's almost like another, like instead of just having the sigma and the rate, you also have to have essentially these alphas.
You have it for both, right?
Right, exactly. It's like
yeah.
It's like almost you're over parameterizing everything just so you can get an answer.
Well, I mean, you need to parameterize your policy either way. I mean, whether you choose to parameterize it as an open loop tape where you have 250 parameters or something like that, you still have chosen a parameterization. I mean, you picked a lot of them. But you need to represent it some way. And so, yeah, I mean, it's whether you do backprop or anything, you're still going to have that exact same problem. I mean, you could do backprop and make it more efficient if you had 5 parameters too, but it also can handle these big open loop tapes and stuff like that. So there's less of a pressure to find concise and sort of compact representations. But yeah, but I want to emphasize that these are different ways of looking at it, but the update's the same, the algorithm's the same. The only difference is am I following this local true gradient? Am I following the expected value of my cost? Right. All right, so some toy example here to show some of the practical issues of some of these things. And please, if there are any more questions about any of these things, even if, it seems tangential, just let me know. Okay. So here we have the algorithm we just talked about implemented. You can see how simple it is right here. I'm doing a for loop instead of that while converged, but we have a loop through some number of iterations. I get my sigma and eta. So this is so I can make it dependent on the number of iteration or something like that, so I can make them decrease. I generate the noise according to a Gaussian distribution here. I get my reward. And the rest of this is just sort of plotting stuff and everything like that. And then here's my update. And that's where I update my baseline, right? So you can see that this is just so that pseudocode right over there. There's like nothing more in it. All these functions are just so that I can switch between different things really quickly. But it's very easy to implement.
Wait, so you do use a baseline, but in the equations, it was just j of alpha plus c.
Right, I mean, this is what pops out when you look at that expectation. But as we said, the expected value of e is 0. So if I have a constant in there, my expected value, if I subtract off that constant the same way, it's not going to affect the expected direction of my update at all. So these say you don't need a baseline, but a baseline has performance benefits, right? So that's sort of another, as you go these different directions, this one says, oh, that you don't need a baseline. You can put it, it helps. The other one's more natural to think about starting with a baseline. Then you can say, oh, well, you actually don't need it. So again, they both have the same effect there. Maybe I should have been more clear, but yeah. Right. So the problem that we're looking at is simply, we have a spline, so I make a spline, and then we're trying to figure out a curve that gets as close to that spline as possible. All right, so it's really just sort of we're trying to fit a curve to this random spline, right? Now, obviously you don't need to do anything fancy for this, but it's very visual, and so I think it's probably a good example here. So we'll start. The cost function we're using is the squared distance between our like sort of guessed curve and the actual curve. And try running it. All right. So on the left, this is our cost. Well, we have it formulated as a reward here, so it's a negative. And then over here, the blue thing is the thing we want. The red is our nominal, and the green is our noise. So you see our noise is pretty small. I started it at all zeros, and you can see it climbing here, right? And it is getting better. It's bouncing around a bit. But yeah. And so this is actually parameters as a spline, so it could be exactly correct if we let it. I mean, it's capable of representing the curve exactly, so the cost could be 0 effectively, right? I think it actually, if I run it and it gets stuck in a local minimum, which is a good cautionary tale, it's even the problem simple like this, you can still get stuck in local minima, so always be careful for that. But see, it's actually doing a reasonably good job, right? Now, you might be like, oh, well, it has an ideal parameterization. It's the minimum number of parameters you need to have a spline that can represent it. And this will the same form of spline. So that's a pretty solid parameterization. But we can try a different one. This computer is showing its age. When I ran these tests on my desktop, like it went, and so I had my like number of iterations like several thousand. And then when I realized I was going to have to do this, I was like, oh. So, yeah. All right. So here, what parameterization do you want? Linear interpolated, nearest neighbor, a polynomial. All right. Okay. What kind of error is that? There you go. Sorry about this. Well, it's not done. There we go. But you see, it's capable of learning. You know, this is a obviously inferior parameterization. It can't represent the right answer, but you can see it is getting closer here. It's not doing a bad job, right? And the question of what the optimum is here, you know, it's not going to look just like the curve because it has to sort of balance these competing things of the going over and going under. So this is a good example of where your policy parameterization doesn't capture the true optimum. And so when this thing converges to something, it maybe is the best, but it's only the best with respect to that way of parameterizing a policy, right? So if you guess that nearest neighbor is rich enough, and then you put it in here, you're going to see that it's not optimal, right? That you've limited yourself. And sometimes, I mean, the other one with the spline, you put yourself in the regime where you have a very good parameterization, and you can get very close to the right answer. Here we have a poor parameterization. And so it's still going to learn, it's still going to converge, but it's not going to be as good. So lin and terp we can probably do better, but here. Now on the, yeah, we'll go back to, we'll keep it at nearest neighbor for all. You can see lin and terp because we're going to check something else. All right. Now I said previously that this is partially nice because it's robust to noise. So here we're going to look at, we're going to add a Gaussian noise with a standard deviation of 20. Let's see. Now here, it's not doing well. I probably have to reduce my sigma and eta. See if you can get back to where it started, right? Yeah.
I think that it's going to be 400 though, right? You multiply it by 20? So it's going to be
That's the, no, if you multiply by sigma, standard, like the variance is sigma squared.
Oh,
yeah. So yeah, so this is not doing a great job. You can see noise can break it. If we start with a bigger error though, I guess it's effectively shrinking the standard deviation. Also, maybe our eta could have been too big because we're getting big measurements just from this error. You know, so like a big eta. Let's try reducing our eta. So it didn't get worse. If it gets, learning is going to be slow though, obviously, because it has such a small signal. But yeah, you see, at least we prevented it from doing that terrible thing. That's just because it was getting these giant measurements of error and updating based on them. But an expected value will still go where you want it to go. So if you did a bunch of updates, you'd be fine. But that's just because you're averaging out. Yeah, if we reduce that down to, let's say, learning here may be really slow, so let me turn off plotting. I'm sorry about this. I don't know what just happened. Okay. So let's see how this does. There. This is smoothed. I ran a boxcar filter on it. But see, it's not necessarily learning quickly, but with that noise, it still learns. Now, if we're going to be doing this, we might as well kick ourselves back up to 20 and see if we can do anything. Yeah. So there, it's got enough noise that it's sort of random walking a bit much, maybe, you know. If you make your eta small enough and stuff like that, maybe make your sigma bigger so it gets a bigger signal when it measures the change, you might be able to be okay. But, I mean, you can still suffer from these things, definitely. Now, another point here, I talked about cost functions a bit yesterday. Here we have one where it's the square distance. Let's say I think I'm going to give away whether it's going to do better or worse by having named it poor grad. But this one, we're going to get a reward of 1 for each point that's within 0.05 of the desired point. So if you're far away, it's 0, and if you're close enough, it's 1, right?
So it's not smooth.
Right. Where did I? Oh. So you see, this is a much shallower performance. It still looks like it's learning, and it is, because I mean, even a bad cost function can learn. But now I'm going to show you what that looks like when you run it and actually look at the plotting. You see? Now we can give it our, now we're still giving it that linear chirp. Let's say we give it the better parameterization, see how that does. You can see they're not learning nearly as quickly as the other cost function did, right? Let's get all our things back. We can make eta a bit bigger. Let's make it. See? So here the only thing that changed between our runs that looked pretty nice and this run right now is the cost function. Right? You see, it is over the course of, that's at 300 or something, it is getting up there, but if you remember the other one, it's fitting a lot nicer. Right? And the thing is that if you look at probably the cost for the other one, even using this cost function, once you solve it with the other one, it'd be lower as well. Do you see what I mean? That the problem that if you solved it with the other one, then evaluated this cost function on the solution, that would do better than this after some number of parameters. And it's because learning based on this is hard, right? You can see that this is very coarse. It's very easy just to lose one or gain one. You don't have good gradient information. And so this is a bad cost function for learning, right? The same task, even if you were to, if this were the task you really cared about, formulating it with the other cost function, solving it, you actually probably could do better than solving it with this directly, right? And that's because the gradients of this one are poor. It's not easy for it to find the direction it's supposed to move in. And it's even worse. I was talking before about how you could be in regions where you're getting zero cost, or zero reward for a while, or there's no gradient at all. So if we start ourselves with an error here, it's not getting any measurement. You see? Like it's not changing at all because it can't measure anything. So if we go to, I said the way to solve that, if you were stuck with it, could be to use more violent kind of sampling. And there you see we actually are able to get at least some reward. And it takes a while, but you see that there's more violent sampling, at least getting out of that region where you don't get any information, right? Still not the best, but if you're stuck with that problem, that's one way to deal with it. But you can see that with the other one where it doesn't have any regions like that, if you go back to our nice grade. Whoa, sorry, I need to switch my eta. Yeah. Whoops. All right. We can go back to. See how much nicer that is? So there you go. So here you can see the parameterization can affect it a lot. The cost function can affect it a lot. The eta and sigma can affect it a lot. There's a lot of concerns, right? And that's why something that should make SNOPed and stuff more appealing to you. Because if you can compute those gradients using backprop, there's no guesswork in that, right? You give that to SNOP, There's no parameters to set. I mean, I guess there's some convergence criterion and stuff, but you don't have to play these games. There's a lot of ways to get this wrong, right? So
So the reason that he introduced the non-deterministic policies was a way to explore. That was the only reason?
for here, I mean, they provide you with exploration, yeah. There's certain situations, like we talk about gambling and stuff like that, where stochasticity, like if there's an adversarial kind of opponent, stochasticity can be necessary for optimality sometimes, right? But in these kind of cases, like where you have a dynamical system, like I don't see how stochasticity in a deterministic system could make you more optimal than deterministic, right? That's because the system is deterministic and not trying to guess what you're doing and stuff, though. So that's pretty nice convergence right there. Yeah. And you see, if we evaluated this solution with our cost function of that, of the one with poor gradients, I mean, this is going to do a lot nicer, right? And that's just, even though like we wouldn't solve it explicitly, it's just because the gradients of this one are a lot nicer, so you can solve it a lot nicer. So remember that, is that cost functions, even if it's not explicitly what you maybe most care about, maybe you just care about, for example, we care about catching the perch, right? But if we want to catch the perch, it could be that by learning with something with like a distance in it, maybe we'd learn better and actually end up catching the perch more than if our reward was just 1 if you catch the perch, right? So cost function design can matter a lot. Policy parameterization matters a lot. So hopefully that you all feel really comfortable using stochastic gradient descent now in the situations where it's warranted. Yeah.
Can you talk a little bit about the baseline part? Like, how did you do the baseline?
Yeah, my baseline here, I think I have 2 implementations. It's something that we can do. So my baseline here right now, I'm using a second evaluation, right? We can do an average baseline. I just screwed something up. It's going so crazy, but we'll try a smaller eta. There. So yeah, so this is an average baseline. See, it's still improving. It's not doing as nicely. That's also because we have to turn down the eta and stuff. I don't know what that error was. I'm not going to try to debug it right now, but you can see it's still learning. Right. Now, the real question is, what if you have no baseline? Right? We need a really small eta there because now it's not getting rid of anything. See, that's enough. Yeah. You don't really have to turn it down even more. But that's a good example of why a good baseline is so critical, right? I mean, you can see that all we did was change how the average baseline was working fine, and it didn't cost us any more. We didn't have to do extra evaluations. And then we just got rid of it, we put in that, and you see how much it struggled there. So I mean, if you just do an average baseline, you get it for free, and it's still a huge advantage over trying to do it without any baseline at all.
Although we did, I mean, it will eventually work without any baseline, it'll just be a lot slower.
Yeah, I mean, it should. I mean, the thing is that in practice, it can random walk around and get stuck in weird places. Like right here, you see, this is that. It had a big run of improvement there and did better than it originally did. But you see it's just walking all around. And so yes, I mean, there's still this bias towards improvement, and it will work. And if you were to calculate a whole bunch of delta alphas and then average them all together, then you probably wouldn't walk in the wrong direction as often. But here the thing is, you have to remember that it's sort of always moving in the direction, right? It's moving more or less depending on how good it is. And so yes, this should still work. But in practice, it doesn't, yeah. In practice, a good baseline helps a lot, as you've seen. So hopefully all those examples.
Is it also the case that a bad baseline will not hurt you a lot? Or if you have
well, how bad? I mean, this could be considered bad, right? A zero baseline could be bad.
Is that a worse baseline though, or could you actually have a baseline that gives you worse results than no baseline?
You probably could, because you could just have it be a bigger error, right? Just more in the wrong direction.
Right.
Right. So yeah. But I mean, that's what I'm saying. If you average over the past several trials like we did, and then reduce the rate of your learning so that those averages are relatively representative, and you don't move too much when you're wrong. Yeah, but I'm saying, yeah. I mean, an average baseline is free. There's no extra policy evaluations, and it still helps a lot. So an average baseline makes sense. And I mean, in something like this where it's so cheap, like if you want those big jumps and stuff like that, like the average baseline is, if the big jump can struggle, because the cost is so different when you've updated, right? So your average doesn't necessarily make a lot of sense. But so there sometimes it can be better rather than reducing your updates, like when we were really far away from the right policy, and we had like a long way to move, and we could like move in all sorts of ways that would still be good. The average baseline, if we turned everything down so the average baseline still worked nicely, that probably wouldn't be as fast as doing 2 policy evaluations and doing big jumps, right? Where every time it just reevaluated. And so yeah, so there'll be, to move it like smoothly with an average baseline, it may take more than like twice as many iterations as the one does when you do a ideal baseline. That's something that I've seen in practice, is when you're doing these like big updates, a real evaluation can be fewer evaluations in the end. So, anything else? Or anything else you'd like to see run on the spline fitting problem right here? Yeah. Anyone has any questions? We're all good? You're all gonna tell Russ and that you understand stochastic gradient descent perfectly, and yeah, it's going to be extremely useful in your research, and the problems to which it is well suited. All right, great.